Hi, my name is Wrenna Robson, and I want to talk with you today about my summer project, Formal Specification of Isogeny-Based Cryptography. By the end of this presentation, you'll understand exactly what I mean by that, but first, I want to talk to you about Ronseal. Ronseal's a brand of DIY sealants. The old Ronseal slogan was, does exactly what it says on the tin. If I get something that says it's rainproof 30 minutes, so they claimed, then by goodness it would be rainproof in 30 minutes. I shouldn't expect it to be rainproof in 20 minutes, and it might not stand up to pressure washing, but it will be rainproof after 30 minutes. So there's two things here, right? Firstly, the Ronseal tin is precise about what it does, and secondly, hopefully, it does do that thing. Okay, so suppose I'm developing a new cryptographic primitive or protocol instead of a DIY sealing or proofing product. I promise this is going somewhere. So what should I put on the tin for my cryptographic thingy? And how do I get the Ronseal guarantee for what it says? How do I know that it really does do what it says on the tin? Now, this is a hard problem. You can tell it's hard because people keep finding bugs in cryptographic implementations. The heartbleed bug, a critical security flaw in OpenSSL, stems from a buggy implementation of the heartbeat extension. OpenSSL's heartbeat was not what it said on the tin. There was a mistake in it, and that meant that it behaved in ways that the written specification didn't account for, and that created a flaw. So this is a hard problem, and it's also important. What are some solutions? There are a bunch, but I'm not directly going to talk about this notion of how do we get a Ronseal guarantee first. I want to first talk about writing on the tin in the first place. So consider a cryptographic specification. We can think of a specification a little bit like what's written on the tin. It tells us exactly what a cryptographic protocol primitive does, how it functions, how it should be used, etc. So consider some code which is like the implementation of a specification. This is what's in the tin, right? That's the actual implementation. If someone else wants to produce their own implementation, let's say they want to write a different version for a particular embedded system, then that implementation should also have the Ronseal guarantee. It should do what it says on the tin. It should fit the specification. Okay, well, how could we do this? Well, we could write tests that it must pass, that it must successfully encrypt random values that we send, or get the right outputs on known inputs. That seems pretty reasonable. That seems like a way to test for correctness. But that doesn't quite work. It might be that part of the security proof of the original specification relies on a particular way of performing some method, or that there's some edge case that isn't often encountered in random or in pre-selected inputs where they differ. So ideally what we need is some way of verifying that the two implementations do what they say on the tin, that is robust and maybe even automatic. And one route to this is what's called formal verification. Formal verification means using formal mathematical methods, often automated by a computer, to prove the correctness of some algorithm. Normally you'd say that this is with respect to a certain formal specification. Well, what does that mean? Well, go back to that written specification for a moment. This is a PDF, and it's what's written on the tin, right? But it's written in human language. It's written for humans to read. It's ideally precise and unambiguous, and we're certainly going to have a problem if it's not. But that is really hard to achieve perfectly in natural language anyway, and it's not necessarily going to be in a form that a computer can use. The thing with the Ronseal metaphor is it's nice and simple to read what a tin claims, but actually, if we're dealing with the specification of an involved, complicated algorithm, maybe not so much. So, if we hope to use formal verification to get our guarantee of correctness, that it does what it says on the tin, we need a formal specification to compare it against. And that can't be in English, in any natural human language that's not easily parsable by a computer. So what could it be in? Well, there really are a number of options for this. There's different languages which you might use in different kind of contexts. Too many for me to really get into right now today, but the one I want to talk about is Cryptol. Now, Cryptol is a domain-specific language. It was invented for a particular purpose rather than designed for general use. That particular purpose was for specifying cryptographic algorithms, and it was created by a company called Galois Incorporated, originally in the early noughties, although it has been refined and changed over the years. I don't want to go into too much detail on the specific features of Cryptol as a language. It's a functional language, a bit like Haskell, though with a stricter type system that forces you to care about the sizes of types. That doesn't mean much to you. Don't worry about it too much. The important thing to know is that A, the natural way to write crypto code is sort of in terms of smaller procedures and instructions that you then fit together. And B, if used right, crypto can absolutely completely specify many common cryptographic algorithms, though it does cope better with symmetric cryptography. Now, crypto actually used to perform verification as well, that the checking that it has the Ronseal guarantee, that it does what it says on the tin. But actually those functions have been spun off and extended into a tool also by Galois called the Software Access Workbench, or SAW. SAW lets you take, for instance, a C implementation, compile it to bytecode, and write a proof script which compares that bytecode against the formal crypto specification, checks that it satisfies properties, checks that functions do the same thing. That proof script, that's the verification. That provides the Ronseal guarantee. That's the dream. So that's what formal specification is. You should now understand that formal specification of a cryptographic algorithm means creating a precise computational model of the algorithm and its properties so it can be verified and we can get a guarantee of correctness. You've probably worked out that this is what I did in my project. But what did I specify? Well, yeah, looking at the title, yeah, it's this thing I've called isogeny-based cryptography. What does that mean? Well, I'm going to try and give a very potted explanation. So this is an elliptic curve. This one's over the real numbers, so it looks like a curve. It's all like curvy and stuff. I can graph it, and actually it's got a nice addition rule on it. So I can think of this as a set of points in space, and there's a way to add points together to get a third point in a way that works like addition kind of should do. It obeys all the rules we want addition to obey. This rule looks something like this. Take 2 points, draw a line through them, hit the curve in a third place, draw a vertical line down from that point until it hits the curve again. That's your addition. That seems quite odd. It turns out this is like the correct thing to do for technical reasons I won't get into. So none of this is new to you if you're a crypto person, but this is kind of a more general audience, so I'm just trying to get everyone to the same place. So just do bear with me. So let's say I pick some random number n, a point p, and I calculate np, p added to itself n times, and give you the result q and the point p. Can you find n? So the answer is, it turns out this is hard enough in a kind of cryptographic sense that we can base cryptography off it. Here's an idea for how we could use this for something useful. Let's both start with a point P on some elliptic curve that we agree. I'm going to pick a random number n, you pick a random number m, n and m. I calculate np, call that q1, and you calculate mp, call that q2. So then we exchange q1 and q2, points on the curve. Now I calculate nq2, you calculate mq1. Okay, so I claim we now have the same final point. Think about why. Well, I've calculated n copies of m copies of my starting point P, and you've calculated m copies of n copies. But these are the same, because m times n is n times m, which you learnt like when you were very small. Okay, this is quite nice. We don't know each other's n and m, but we sort of managed to share a secret, this final point we've ended up with. Before I was talking about doing this with the real numbers, but that might not work so well, right? Floating point numbers can have error terms and things. We need this all to be exact, so we definitely end up with the exact same point at the end. But that's okay, and actually what we do in practice, we actually define this elliptic curve over something called a finite field. It's like a finite set, but one where we can still do addition and multiplication and kind of things that look like arithmetic. You can't really visualize it like a curve in the same way, but we are going to use that because it helps us think about it. So perhaps I have some kind of hash function or something that can take a point and return some maybe pseudo-random string based on that. Okay, so now we have the same one of those because we've got the same final point, and we've got some kind of shared secret derived from that shared point, and maybe we can use that as a basis for symmetric encryption. This could be for shared key, for instance. So what I've just described, just to be clear, is not new at all. Very old. It's a process called Diffie-Hellman key exchange, and pretty much most, for instance, modern internet browsers will use a version of it when they connect your security to websites, or certainly they can do. I'm describing it because it's useful to understand my analogy to the next thing, which is what we really want to discuss, isogenies. One last thing you should know, every elliptic curve has a magic number called a J invariant associated with it. You can calculate using the equation of the curve. How you do that isn't important, just remember it exists. Okay, so everything so far has been on some specific elliptic curve that we pick and operations on points on those curves, but we have lots of elliptic curves and they kind of form families. So now let's think about the curves themselves instead of the points on the curves as things we can move between. How could we move between the curves? What would that mean? Okay, things are going to get slightly more abstract here. Again, bear with me. So here's the idea. Curves are just sets, so we can define any old function between them. But actually we want special functions, functions which preserve this nice notion of point addition. So if we add 2 points together and then sort of move them to another curve, that should be the same as moving them and then adding them. We also want it to be nice with respect to the geometric properties of the curve. We don't want this transformation we perform on our coordinates to do anything particularly weird. We just want it to be like polynomials divided by other polynomials. So we're going to call functions which satisfy these this nice enough function properties isogenies. So curves have isogenies from themselves to other curves. Actually, isogenies come in what's called dual pairs, which means I always know, if things are sufficiently nice, that if I have an isogeny one way, there's an isogeny the other way, and these have some nice relationship between them always when they're kind of a dual pair. So actually, sometimes a curve will have a special kind of isogeny to another curve, which means if you combine over its dual, it's like doing nothing at all. And these are isomorphisms. So curves can be isogenous to one another, and if I can go one way, I can always go the other way. But some isogenies are special, and it means the curves, when I go one way and then the other, it's like I've not really done anything at all. And curves where we can do that, we call those isomorphic, and the maps between them isomorphisms. And for most purposes, we could treat them as the same as one another. So we can actually constitute a family of elliptic curves that are all isogenous to one another. I can get to them via some isogenies constituting a graph, which might look something like this. I can move from curve to curve along mini isogenies, and then the isogeny from like one curve or one side of the graph to the other side is the result of doing all the isogenies along that path. A few more things I want you to know. Firstly, it turns out there's a neat way to characterize and calculate an isogeny in terms of special subsets of the elliptic curve, which means I can stop talking about kind of abstract functions and start talking about kind of actually very specific small subsets of the elliptic curve that give rise to it. This is computationally convenient for one thing. Secondly, curves are isomorphic if and only if they have the same J invariant, that number I mentioned before, which means if I kind of was only thinking about J invariants, that kind of justifies treating isomorphic curves as the same, and that is what we are going to do in the end. Thirdly, this is the most important thing. It is hard to calculate an isogeny between two elliptic curves which are isogynous. In other words, if I pick two random points on this graph, it's actually quite hard without the whole graph as a map to work out how to get from one to another. Okay, so with points on curves, given 2 points, one which was a multiple of another, it was hard to work out what the multiplying factor was. With curves on the isogeny graph, given 2 curves, it is hard to work out what the connecting isogeny is. In the first case, we could use that hardness to build a key exchange. Can we do the same with isogenies? The answer is yes, sort of. I'm not going to go again into the precise details here. We need a lot longer, but essentially, yeah. I can basically choose an isogeny at random from some starting curve, and you do the same thing. So we start at a curve we agree on and do 2 random isogenies, which you can kind of think of as basically both doing a random walk on the graph. We get to wherever we get to on the graph, we get to whichever curve we've gone to, then we exchange the curves, and then we do our random walk that we had before again. So hopefully you can see this is kind of analogous to what we did before on the points, although it's not quite clear what it means to do the same isogeny or the same random walk but moved. But we can make that precise and do it, but we do need to exchange a little bit of extra information. We can't just say this is where I am. We've got to pass along some extra stuff to help us continue our walk. Again, I won't go into the details there, but it is important to realise that means you exchange a bit of extra information, and that actually might make the underlying mathematical problem easier, potentially. So you can wake up now if you've zoned out a bit. I'll try and summarise. I do some random walk A on the graph of isogenies. You do some random walk B from one starting curve, E0. This gets us to, respectively, EA and EB. We exchange these with each other, plus some extra information to help us navigate. And I do walk A from EB, and you do walk B from EA. Let's say I end up at EAB, and you end up at EBA. Then they might not be exactly the same curve, but they are going to be isomorphic, it turns out, as long as everything is working sufficiently nicely. We managed to set some preconditions, and that means that they'll have the same J invariant. Well, now we've got a shared secret. J invariant is just a number, and then we can use that in the same way that our shared point before allowed us to maybe derive a key. We can use that. The key here is that we've shared some information secretly without actually telling each other our secret key. We call this process supersingular isogeny Diffie-Hellman, or SIDE. SIDH. Super singular just means a special kind of elliptic curve that will actually make this work properly and give you the right security. I won't go into that. And Diffie-Hellman because it's analogous to the Diffie-Hellman thing that we looked at before. Unfortunately, Psi doesn't quite have all the security properties we want it to have. In particular, I don't think it's CCA2 secure. You can, though, fix that with a standard transformation with some hash functions that sort of form a wrapper around it. And in using that, we can turn Psi into what's called Sike, S-I-K-E, super singular isogeny key exchange. Now, there are other cryptographic systems based on isogenies, but Sike was the one I explored for my project, and it's an important one because it was in the second round of the NIST post-quantum standardization process, and it's now an alternative candidate in the third round. Okay, what does that mean? Right, glad you asked. So, you might be wondering why, if this does something very similar to that simpler thing that we did before, why can't we just use that? I mean, I said browsers already use it. So the answer is that the hard problem at the core of that was, given points P and Q, which is NP, find N. This is called the discrete logarithm problem, incidentally. That's fairly trivial with a quantum computer using something called Shor's algorithm. There's a need for so-called post-quantum primitive that fill various niches, which will be secure even when we have decent quantum computers, which, by the way, hasn't happened yet. It might not ever, but we definitely want to be future-proof for it if and when it comes. So NIST, the National Institute of Standards and Technology in the United States, is holding a multi-stage, long standardization process to try and agree and standardize promising candidates to fill this niche. Psych is one of these candidates. It's now at the third stage, so it's an alternative candidate. It's not a finalized for standardization, but NIST want to encourage its continued development, in part because no other candidate is isogeny based. And you kind of want lots of different algorithms that are based on different hard problems in case they actually turn out to be easier than we think. So you now understand what formal specification is, and you now know what isogeny-based cryptography is, and I've actually mentioned specifically cryptol allowed you to do formal specification, and Sykes an important example of the latter. So yeah, what was my project? It was precisely using cryptol to specify Psych. And then actually also try to validate that using SOAR, the Software Access Workbench, against the reference implementation of Psych. In other words, I had a tin, I needed to work out exactly what should be written on it, and then I was hopeful of maybe trying to prove at least some of the Ronseal guarantee. So what I haven't done is actually explained how my project went. I want to give a quick summary of that. I started by looking at a couple of other NIST candidates, Rainbow and Bike, before settling on Psych as I had a pre-existing interest in it, and I thought it seemed most amenable to specification in cryptol. Cryptol doesn't cope well with data in certain forms that occur naturally in Rainbow, and I haven't worked out how it best does non-deterministic algorithms, which is sort of inherently hard to specify in a functional style, which meant I couldn't quite get to grips with Bike. Psych, however, is sort of fundamentally based on layers of mathematical operations on increasingly abstract objects. A finite field, a quadratic extension to that finite field, elliptic curves over that quadratic extension, isogenies over those elliptic curves, hash functions layered on top of those isogeny operations. So it seemed a great candidate for implementation using cryptol, because cryptol and functional languages in general sort of, in my experience, fit quite well into that paradigm. I was right in this. It took a while, maybe a couple of months, to learn cryptol properly and get all the details ironed out, but after that time I had a working specification in cryptol of Psych. It was slow by a few orders of magnitude compared to the C version, but it worked. My next task was some optimization and tidying up. The bits I'd done at the start were the most untidy, as happens when you're writing code, and then a decision to either specify another algorithm or try verification on my cryptol specification using SOAR. As I've already mentioned, I chose the latter. This turned out to be quite tough. Actually tough enough that while I made some good progress here, this part of the project wasn't ultimately successful in the sense of producing a fully working outcome at the end. But I feel like it was successful in the sense that part of my goal was to explore how difficult it would be to use SOAR for verification. It was itself informative. Good research doesn't have to result in a definitely working product at the end. My issues were that SOAR does not really accept arbitrary position integer types very easily, and Psych uses very large integers. After about a week trying to work around this, I had an idea, which was this. I could maybe create a toy version of Psych, one where the parameters were much smaller, which would not be usefully secure, yes, but given that the only difference would be the time taken to do the computations, this would, in theory, be useful. I had written my specification in a parameterized manner. So once I worked out how to generate suitable parameter sets, this wasn't so hard. I also decided to implement only the side part, focusing on the isogeny arithmetic rather than the hash function wrapper, which simply used shake256, which is sort of based off SHA-3. I also had to adapt the C implementation that the makers of Psych had provided. I didn't previously have much experience with C at all, so this required me to learn a lot of C quite fast. I bounced off it before, but never really got very far. This was tricky but very fun. I now understand pointers, which I'd never really got before. I don't come from a computer science background, so it was a really useful outcome of the project process for me, this. Having made my cut down C implementation and my toy size specification to match, I then began to try writing a source script to provide the Ronseal guarantee that they did the same thing. I'd refactored and rewritten both so that their corresponding functions were as close to each other as possible. This worked quite well for the simpler functions, the basic field arithmetic, but once I started hitting some of the more complicated ones in the quadratic extension, for instance, it began to hang when I tried to prove them. That's very possibly because essentially it just couldn't prove bytecode equivalence using any smarter methods, so I just had to resort to checking every case, which is just computationally impossible. I made some good progress by learning how to tell it to reuse proofs it had already done when functions were used within other functions, but by the time I got to the end of the time I'd allotted for it, I still hadn't finished it. The documentation for SAW is a lot less developed than the documentation for crypto, so again the learning curve here was quite steep. If I had had more time, I think I would have probably got further with it. It wasn't that I just ran into a block I couldn't get rid of, but ultimately I decided I wanted to start writing up and do a really good job of that, rather than spend all my time hitting myself against a programming wall and then have a rush at the end. And this was the right decision. That is broadly an account of what I was trying to do in my project, what it was about, and how it went. It feels essentially successful to me. I didn't achieve all my stretch goals, but I certainly learned a lot from it, and I did produce something quite cool. I found the whole world of formal methods, of which specification and verification just one part, really interesting. And actually it's my intent to learn more about it and perhaps make this area my research focus going forwards. It just really lit a fire in me. I found the whole experience taxing at times. Days and days of struggling over code in lockdown got a little grim, but ultimately it was really rewarding and fascinating, and I hope I've shared a little of that feeling with you. Thanks for watching, and I'll see you at the Viva.